Hello, I want to use this video to go over these two practice problems using the Boltzmann equation to calculate the change in entropy. Let me read these two right now, then we'll go over a couple notes and then we'll tackle the problems. Problem number 1, in an experimental setup, an oxygen molecule is absorbed on a surface which has 400 absorption sites. Then imagine that additional surface becomes exposed so that 576 absorption sites are now available. Think of the expanding number of sites as more microstates. Calculate the change in entropy. Problem number 2. What is the change in entropy for 1.0 mole of an ideal gas originally confined to 1/2 of a 5.0 liter container when the gas is allowed to expand at a constant temperature? Okay, let's jot down the Boltzmann equation first and remind ourselves what each term means. The Boltzmann is S equals K, the Boltzmann constant, ln of W, which we'll think of later as the number of microstates. There's actually something in previous videos that I have not discussed. I've definitely discussed the Boltzmann equation, and I've given the Boltzmann constant. Boltzmann constant is 1.38 times 10 to the minus 23 joules per Kelvin. But what I did not tell you is that this comes from the R, gas constant, divided by Avogadro's number. That might have been very good to know previously. 8.314 joules dot mole minus 1 times K minus 1. So those would be in the denominator. You know Avogadro's number as per mole, particles per mole. 6.02 times 10 to the 23. I won't put particles, but it's anything per mole. So the per moles cancel out, leaving us joules per K. W. W, you've heard me say before, it's the number of energetically equivalent different ways to arrange molecules. Number of energetically equivalent different ways to arrange molecules. In a previous video, we call this microstates. And we had a little exercise where we were looking at all the different microstates that 4 molecules can assume. Okay. Now, if you think about that problem number 1, we have a change in the number of absorption sites, and I've hinted that we should think of those as different microstates. So there's a change. So really what we're doing is the change in entropy equals the S initially, no, it's final minus initial, S final minus S initial. Okay, so that's standard for a delta term, but when we plug in the final and initial here, it's basically the final Boltzmann equation minus the initial Boltzmann equation. And when we rearrange that, remember when you take ln of something minus ln of something, it's really the ln of that value divided by the initial value. Let me stop talking. Let me just write it down. This should make a lot of sense for those of you who are strong in math. Equals, actually let me write it underneath. I'll write it here. Delta S equals K ln number of microstates final divided by my number of microstates initial. That's the equation that I would put on an equation sheet. This is the equation we'll be using for problem 1. Those are your differences in microstates. Okay. Very simple, plug and play at this point. What about problem 2? Problem 2 gives us information about the volume. And you can tell, right, that the change in entropy will be positive because, wait, would it be positive? Yes, it will be positive because we start out with the molecules in only one half of the container and then we let them expand. So we're gaining in disorder. It's a very good idea to have an approximation or at least know the sign of your delta S before you start a problem. You're gaining disorder, therefore delta S is going to be positive. Just like here, for problem number 1, delta S is going to be positive. Okay, so what's going on in this equation? Because now we're working with volumes. In a previous video, I told you that the number of microstates equals x to the n. I'm not going to put this in the square box. We're just going to use this to help derive a modified Boltzmann. But the x is the number of cells, and the n is the number of molecules, not the number of moles. I really hope I didn't get that messed up in the previous video. It's the number of molecules. Okay, we're going to use that. We're also going to use the fact that the Boltzmann constant came from the gas constant divided by Avogadro's number. Okay, good. Avogadro's number. Lastly, we're going to use the idea that the total volume, okay, good. So problem 2 talks about volume. The total volume equals the number of cells, which is obvious, times the volume of each cell. So this is obvious. Number of cells times the volume of each cell. Now don't worry about the number of cells, because they're going to cancel out when we combine all of these and derive a new modified Boltzmann equation. Volume per cell. And what we're really concerned about is the total volume, right? We go from 1/2, so that's 2.5, to 5. The volume is getting doubled. Okay, so don't worry again about the x, and you don't even have to worry about the number of molecules. We're going to combine these terms to get rid of those values, rid of those parameters. Now, I'm not going to show you the derivation, but you know, what could you do? You could replace k, right, with this. Eventually, we're going to replace the number of cells when we divide, then final minus initial. Ultimately, this is the equation that I would put in a box on the equation sheet. Delta S, change in delta S, equals n r ln of v final over v initial. And if you recall problem number 2, we have v final and v initial, and we have the number of moles, n. So everything is there for us to do this calculation as well. let us label what these variables are. Number of moles. R is, you're not going to change it, it's 8.314. And again, it's joules per mole dot K. And then these volumes can be any unit as long as they're consistent and the units will cancel out. So just like here, the ln of the microstates, that's unitless. And the units of entropy will be the same as the Boltzmann constant, joules per K. So that makes sense. Over here, let's do the unit analysis as well. That is unitless. And then we have moles times the gas constant, but see how the moles cancel out? So we're also left with joules per K. Okay, very simple. The derivation could be a little bit tricky, but I don't expect my students to do the derivation. It's just plug and play now, understanding which of these two types of Boltzmann equations you want. One works with microstates, the other one works with volumes. I actually worked ahead and did this. So what you can do at home, let me cover up the answer. What you could do at home is, could you go ahead and plug in numbers for each problem. Problem number 1, right there. And I wrote the equation for us here. Now it's a question of, can you punch in the correct numbers on the calculator, and does your calculator do the operations the way you want them to do them? And then problem number 2, let me see if I could do this without giving away the answer. Problem number 2, and we're using this equation. Okay, go ahead and test yourself. Pause the video and do those 2 problems. I'll show you problem number 1. Okay, let's compare answers. We fill in the Boltzmann constant. Remember, that's joules per K. This is unitless. And then hopefully you can work out the math on your calculator properly. What I would do is, actually, I would do this calculation first, and then say ln of that answer, and then that answer times the Boltzmann constant. The answer that I got is 5.03 times 10 to the minus 24 joules per Kelvin. The unit analysis works out well, and don't forget, in your final answer, write the units. Problem number 2. You have something on your paper to compare with my work. Change in entropy. We expect it to be positive. Just like problem 1, it was positive. It would have been negative, right? It would have been negative if these 2 numbers were switched. Same thing here. The final volume is larger than the initial volume. Let's do the unit analysis in our heads. That's unitless. And then moles times the R constant. So the moles and the R constant goes away because it was in the denominator. Left with joules per K. In terms of order, what I would do on my calculator, I would divide 5 divided by 2.5, take the ln of that answer, take that answer multiplied by 8.314, take that answer and multiply it by 1. Right, so I'm always saving the answer of the previous operation on my calculator, so I don't have to retype it. The answer for this is 5.8 joules per Kelvin. Those are wildly different numbers, but just remember, right? You know, we're only working with one molecule here and a relatively limited number of microstates. Okay, don't get confused by this picture. I never mentioned it before, but this is 16 microstates, just an example of a little patch of the surface. 4 by 4. So that's a very, very tiny number in terms of its change in entropy. But this one is larger, 5.8 compared to 10 to the minus 24. But that's because we're dealing with a mole of gas, and we're dealing with volume now, fairly large volume actually, compared to what you would imagine for this situation. Okay, very simple. Honestly, this might be the last video where I talk at length about the Boltzmann equation. I know what we're waiting for. We're waiting for chemical reactions, comparing delta S, using delta H, the enthalpy, and eventually we're going to get free energy and talk about spontaneity. But that's in future videos.